Hello, everyone. So our final unit for AP Physics 1 is going to be based on electrostatics and circuits. And so we're going to start off with electrostatics. And this is going to be about charge and the transfer of charge and the electrostatic force. So basically, we're talking about the electrostatic force, which I think we've all experienced some sort of electrostatic shock. So whether that is rubbing your feet on the carpet and you touch a doorknob, or even if in the really dry winter times, if I touch my cat and then touch the doorknob, sometimes I'll even get shocked. Things like that. When you take your clothes out of the dryer, you can get shocked unless you're using things like dryer sheets or dryer balls. So what's happening is we have a lot of friction between the objects being rubbed together, and that's basically going to be loosening our electrons, which is what we'll discuss. And so that's going to create a transfer of charge. And really, one of the key words is going to be a transfer of charge. When we have a transfer of charge, it's going to create a force. So there's going to be some parts here where I definitely will skip around. So if we were in class right now, I would use a kit like this, which would have plastic and glass rods. And also we would have like wool type of cloths that we could use to charge and discharge these rods. So for example, if we had two plastic rods, so most things on the earth are going to be completely neutral. So we'll talk about what neutral means. And so that means that they have a balance of protons and electrons. And so these have not been charged. So one thing that you can charge something is through friction, like I mentioned before. So friction, you can loosen some of those electrons, which can charge an object. So these are not yet charged. So we do not see any sort of attraction or repulsive forces right now. So this tells us that they are both neutral. However, now we have, now there's clearly some charge here. We can see that the rod on the left that's hanging on a string is being pushed away. And so we'll talk about how like charges repel. So let's see if I can. So like charges repel. And sometimes we're going to have to gain information by using context clues if there's something like a diagram or something like that. A lot of this chapter is kind of more conceptual. There is some math, which we'll get into today, but that's going to be part of it. Okay, so on to the electric force. So we've only talked about one long-range force before, and that was the gravitational force. And the gravitational force is universal. It happens between every object that has mass, and we know that it varies based on how far away those two objects are. And the electric force, which we'll show you, is really similar. And this is going to be between any charged object. So it doesn't affect neutral objects. It only affects objects that have a charge, or as we'll look into later too, if we have a neutral object and a charged object, it'll affect that as well. So this is what it would look like if we had opposite charges here. And the reason why I can tell that they are opposite charged is because they are being attractive. So opposite charges, I'm going to abbreviate here because doing this is not the easiest thing. It's not as easy as using a pencil or something. But so opposite charges attract. And so I want you to know that I don't have enough information to know if this plastic rod is negative or positive right now. Just based on the pictures with this information, I don't know which one per se is positive or negative, but I do know that they are opposite charge, and those are the types of details that you're going to be looking for right now. So as a visual, as you pull away this charge rod here in the hand, you will see that the amount that this charge rod is affecting the one that's hanging is decreased. And so just like with gravitation, the further away that those two objects are, the less, the smaller the force that affects that object. Okay, so we will be using like diagrams to represent our problems here, or you'll see these in diagrams. And so a negative sign is just going to be used for a negative charge, like a plus sign is going to be used for a positive charge. And if something was a neutral charge, you really wouldn't draw anything, okay? Right now, because there's a balance of positive and negatives, I would just draw a rod. But the interpretation here is that we have 6 extra charges here, 6 extra negative charges here, and we have a +6 charge here on the right. Oops. Okay, so yeah, so here's like a piece of wool and a charged rod, and they're just gonna do a basic experiment here to charge the rod. So right now, this rod is completely neutral. We don't see any positives or negative charges drawn on it. And so that means we have an equal amount of positive and negative charge. So it is neutral. So this is what I was talking, right? So right now, both of these are neutral. And I mean, an alternative way that we could draw this is by drawing the same amount of positive and negative charges, but it's kind of redundant until we get to a more specific situation where it is actually useful. But I think the one on the right, in most cases, isn't necessary. So it's going to be charged through rubbing. And so now, as we can see right here, we have now this is going to be positively charged. The wool is now positively charged, and the rod is now negatively charged. So one thing that we definitely need to learn is that charge is the transfer of electrons. And it's funny, we'll actually see that in the next section, but I think it's really important to state that now. So I think a lot of you have taken some chemistry. So I think a lot of that part you probably already know is that electrons are negatively charged. And so we will take a look at that. But basically, the electrons are on the outer shell of an atom, and they're really lightweight. and they're really far away from the nucleus, which has a very strong amount of force that keeps them together. Okay, so the protons are never move. So it's just the transfer of electrons. Yeah, the protons are attracted by really strong nuclear force between the neutron. So what we can see here is that now that the wool is positively charged, that means it didn't gain protons, but it lost three, let's say 3 electrons. Okay, and so now this rod here has 3 excess or additional electrons. So basically that's how something gets positively charged, is it's by losing electrons, and something becomes negatively charged by gaining electrons. So really, really important to distinguish there. So another conservation law here, and this pretty much like every other conservation law that we've covered, charge is neither created or destroyed, it's only transferred from one object to another. So really important that you know that, just like energy, just like momentum. Okay, I've covered this before with the like charge and the opposite charge. Okay, so this I actually wanted to show you with a few simulations. So I am using a simulation on Physics Classroom right now, and we can use. I really like this demo. Well, that shouldn't be happening. Let me restart this. Okay, sorry about that. I think I can just take away the balloon. Yeah. So basically what we have is we have 2 metal rods, I guess you could say, right now. And the 0 is representing that they are neutral. So they're both neutral right now. And one thing that we need to mention is that there's really 2 classes of materials. And so we have conductors. These are mostly going to be metals, for instance. So these are both made out of metal because they're a metallic kind of color. And what they allow for is they allow charge to flow, basically. Or like move freely. And I'll show you some images in the PowerPoint later on. And then we have an object, which would be kind of like plastics, rubbers, and those are insulators. So the balloon right here is made out of rubber. So it's going to be an insulator. And so it does not allow this charges to flow. So it kind of clings onto them. So charges do not flow very freely. So whenever I bring in the balloon, you'll see that the charges just stay there and they do not move at all. Okay, so I'll keep this on here for a little bit. Actually, yeah. So, yeah, so nothing's gonna happen between them right now. Now, what I'm gonna do is I'm going to introduce the balloon and things are gonna get a little crazy. So I really like this for a few reasons. So the red plus marks are going to be representing the protons. So you can see the protons, they're not moving, they're not freaking out, whereas the electrons are completely freaking out by this balloon being nearby. So you can see they're moving as far away from the balloon that they can because of the repulsive charges. Okay, the repulsive force. And so no matter kind of where I go, they're going to want to move to the opposite side. So I can actually put them in between here like this. Okay. So what I've actually done is I've created a polarization, which I'll show you in another simulation as well. What I've just done is I've taken that negative, the neutral object, and I've now separated the positive charges from the protons and the negative charges from the electrons on opposite ends. And what this kind of occurs is we're going to end up getting a net force between the balloon and the metal rod, but this simulation really isn't built to show that. Okay, so I did take some time to kind of draw this, and we haven't finished talking about the electric force, but let's take a look at what I kind of wrote down. So I'll show this in another simulation, but right here we have the positive part of this rod here, and we have the negative charge of the balloon. And so there's going to be an attractive force between these parts right here. Whereas the parts where the excess electrons are, there's going to be more of a repulsive force. Okay, but this repulsive force is further away. So it's going to be weaker. And so with polarization, we're always going to get a net attractive force. So it's the separation of charge. And like I said, it's maybe I'll do it in text. It's the separation for neutral objects. And any charged object will be attractive to a neutral object. So I'll put that here. That's polarization. Okay. All right. So I am going to move things around now. Okay, so I'm going to clear this. It's getting a little messy. All right, so let's do a few things with this. So what if I were to put these two together and then move the balloon close? Okay, so you can see that as many of the electrons as possible want to move to the metal rod on the right. Okay, so remember, part of being a conductor is that these electrons can move really freely. Okay, now if I were to remove the balloon, they will almost even out. In theory, they should completely go back to being neutral. So it's not completely perfect here. So yeah, if I were to just move the balloon further away, or like take it completely out of the equation, they should more or less return to being neutral eventually. But this is pretty cool. If I move the charged balloon nearby and I keep it there, and then I separate them, And now I get rid of the balloon. Now they are permanently charged. Okay, so right now I have a +8, a positively charged rod, and a negatively charged rod on the right. So what did I just do? This is called induction, and this is one way that this can occur. This is called charging through induction. And so basically the steps here is you have to first polarize. So that's what I did first with the balloon, is I first polarized it. Number two, I brought them together. Well, let's see. That was kind of already what happened. I separated, then I removed the charge. So that's always has to be the last step. Because the first time I did it where I removed and then separated, and nothing happened. So the order of those two steps is really important. And then really one of the last things I want to talk about is grounding. So if I have this right here, grounding. And grounding is going to, it's basically, you have so much excess charges elsewhere, and it's going to kind of restore everything back to being neutral. And so remember that this positively charged rod here desperately wants electrons, okay? Because everything really wants to be neutral. So if I bring this here, you can see that electrons move towards it, okay, to restore it. And why do they move towards it? Remember, if there's such an excess positive charge, and there's electrons here, those electrons want to move to where they're being attracted to. Whereas here, there's so many excess electrons. You can see they don't like being near each other. If I try to ground something, they're going to flow in the opposite direction, right, to remove those excess electrons. So I'm going to show you another simulation just a bit more about polarization. Okay, so this simulation is specifically made to really show polarization. And so this is basically an aluminum can, and this is actually something that's really fun to do in person, so I hate you guys miss it. But it is neutral. You just can't see the electrons are basically right on top of the protons. So what I can do right now is I can introduce a positively charged rod here, and you can see that the electrons just want to move close to it as possible. Okay, so remember, from right here, we have a really strong attractive force from those negative electrons. And then for the positive electrons over here, we have a repulsive force, but it is significantly weaker because it's further away. So the net force is always going to be attractive. Okay. So yeah, it's pretty fun to play around with. You can actually have like a race with this to see like who charged up the rod the most. It's pretty fun. So I can do this also with I'll get rid of the glass rod, and I can introduce a rubber rod, which is negatively charged. Okay, so you can see this time the electrons move as far away as possible, but it's still attractive. Okay, it's still attractive because now it's basically the opposite case. Now we have attractive force from the positive charges, and we have the weaker repulsive charge right there. So we have a net attractive force. Okay. Okay, so we do have some of the questions here to go through. Consider two objects, objects A and B. Object A has a net charge while B is uncharged. Based on this information, it must be true that either A is a conductor, B is an insulator, A is an insulator, B is a conductor, A and B are both insulators, both conductors, or you can't tell. So the answer is you can't tell. So there's not enough information. So just because something has a charge, you know, object A could be either a conductor or an insulator. Okay, just because it's charged doesn't give us any information on that. And B, same thing. It just tells us it's a neutral object. It doesn't tell us anything else. So there's not enough information to make that call. So here's kind of the good diagram that I was kind of talking about here. That's in your book, the one on the right. So kind of see this, I think, on the next picture. Yeah. So this is what I've kind of showed you before. But essentially, you know, the electrons attract, the excess electrons are going to be attractive to the rod, and they're closer. So that's why you're always going to get the net attractive force. So definitely know this. This is a really important thing to know. All right, so right there, polarization force between a charged object and a neutral one is always attractive. Okay. So also very important to distinguish is that polarization is a temporary state. So as I was showing you in one of the demos, it is completely temporary unless you do what I did, which was charging through induction. So it's not a permanent state, really, unless you have another object, another conductor or so, where you could transfer those charges and then separate them. Okay, so I'm going to skip around a little bit so it's not too redundant. But this question is really relevant. So we have positively charged ball, and we can see that it is clearly attractive to the rod. So what can we confirm about the rod? So we need to think about what two ways could there be an attractive force for the rod. So the ball is positively charged. So we know that there could be an attractive force if A, the rod was negative. If it was negative, there'd be an attractive force. Or what we just learned too is that it could be neutral. There will always be an attractive force between a neutral and a charged object. Okay, so the answer is E. Okay, either B or C. There we go. Okay, let's look at this. Okay, so these two metal spheres are going to be touching, 1 and 2. They're touching right here. So these are conductors. They're both neutral. This charged rod is brought near. Okay, so you want to think about what is this positively charged rod going to do? What is that going to do to the electrons? Well, it's going to cause these electrons to want to move over here. Okay, so what did I draw? I drew 6. So for instance, we'd have excess protons on the other side. So I think that's 6. Okay. But let's look at the order here. The charged rod is then removed, then they are separated. Okay, so once you move this away, then these charges will flow back to where they were, and everything will be neutral again. Okay, so I showed that with the simulation there. So the charges on 1 and 2 will be neutral. Okay. Okay, now the opposite situation. Okay, now the only difference is that we're going to separate them after being polarized. So first, it's going to be polarized. Then we're going to move these away from each other. And then we're going to pull away the charge rod. Okay, so I'll just draw fewer of these. So if you separate these, then you're going to have 1 and 2, and they're going to have those permanent charge differences, even with the rod being right here. So then when you move this away, really doesn't affect anything. So, but now 1 is going to be negatively charged, and 2 is going to stay positively charged. Okay, here's a very different question. We have identical metal spheres. We have 3 of them, and they have their charges. Okay. So one thing we can look at is the unit of charge. Okay, the C stands for Coulomb, and N means nano, which is 10 to the minus 9. So this means P has 4 times 10 to the minus 9 nanocoulombs of positive charge, while Q has negative 2 times 10 to the minus 9 coulombs of negative charge. Okay, so spheres P and Q are going to be touched together. Okay, so they're metal, so that's going to allow the flow of charge. So what's going to happen? So how do we solve this is we look at the 4, and we're basically, it works kind of like net force and stuff like that. We're going to add them together. So we're going to add a negative 2 nanocoulombs. So that's going to give us positive 2. All right, now this is going to be evenly distributed amongst them. So after that first touching, we're going to have plus 1 over here and plus 1 at Q. Okay, so after P and Q are touched, that's how the situation is going to look. Then Q and R are going to be touched together. Okay, so Q is no longer negative 2. Q is now positive 1. And R is negative 1. So watch, if we do plus 1 plus negative 1, we get 0. So that means that both Q and R are going to end up being neutral, while P will remain positively charged after this. Okay, let's skim through this because I'm sure you know this a lot already. So we have nucleus, protons, and neutrons. Electrons are hanging out here on the outside. All right, they're really loosely bound. They're in what's called the electron cloud. Okay. So electrons and protons, they are the only source of charge in our universe. Okay, it's pretty cool. We only have charge if we have an unequal amount of protons and electrons. So we've looked at this before. So this is basically a positive ion, so a positively charged kind of molecule here is one that has one fewer electron. A negatively charged one has one extra electron. Okay. The only reason why I wanted to show this is that it's kind of cool. You can kind of see how the molecule can be kind of broken through friction. So you can kind of see the bonds here kind of are like springs, and they can be completely kind of like severed by the frictions, because the friction kind of creates a lot of heat, and then they can be separated. So if you were kind of curious of what this kind of looked at a smaller level, there you go. Pretty neat. So the difference between a proton and electron, and this is pretty neat. So this is what's called the fundamental charge. And so each individual electron or proton has this amount of charge, 1.6 times 10 to the minus 19 coulombs. Okay, so up here in the top, charge is represented by the unit coulomb, which is C, and the symbol that we will use in math is going to be a lowercase q. You will sometimes see an uppercase q as well, which is fine. It's just kind of to distinguish two different objects. So protons and electrons have equal charge. Protons is just positive, electron is negative. But they do have quite a difference in mass. Okay, I mean, obviously they're both really, really small in mass, but the electron is, 10 to the minus 4, even smaller. So, it's a factor like almost pretty close to 10,000. So just put that in perspective. A proton is still considerably much more massive than the electron. Okay, let's take a look at an insulator. So an insulator doesn't allow these electrons to really move. They're really closely or tightly bound. Okay. Whereas, so look at this. So the valent electron, which is the lightly colored teal color, see how close together that is here, and then right here with the metal, it's like a sea of electrons is what your textbook says. And so they can move all around here. They can move anywhere inside of the metal. Okay. Okay, so if there's anything that's the most important that we gather from electrostatics, it's going to be Coulomb's law. And Coulomb's law is going to be the law that describes how electric force is measured and what affects the magnitude of it. So yeah, this is measuring the magnitude of the electric force, and we're going to be given our equation here. So what's super interesting about Coulomb's law is it is very, very similar to the equation that we looked at for universal gravitation, which was like this, m1, m2 over r squared. So they're almost identical, okay? So where with gravity, we had the universal gravitational constant, we now have an electrostatic constant, okay? Which is the value right here. You don't need to memorize this. We'll see on the next slide that you can just use 9 times 10 to the 9 Newton meters squared over Coulomb squared. And before, we had a direct relationship between the masses being added together. And now we're looking at the two charges, okay? And what they share in common is their inverse square relationship with the r squared in the denominator. Okay, so we can see that over here, right here. And these are going to share Newton's third law, so they're going to be equal in magnitude, opposite in direction. So this is what the bulk of our math problems are going to be like. Everything else so far has been really conceptual. Yeah, so we do have the absolute value signs here. So this alone will not tell you if it is repulsive or attractive forces. Okay, so you're gonna have to use your common sense there, you know, whether or not it's two positively charged objects or one's positive, one negative. So it's gonna give you the magnitude, but not necessarily the direction. Okay, so here we go, like with 2 point charges, which is usually what you're going to be using here. The distance between them is going to be r. So you can see that the equal in magnitude, opposite in directions here. And we're just using Q1 and Q2 right now. So if there were 2 negative charges, it would look very similar, repulsive charges. Those opposite charges, like we have in the bottom, they would be attractive forces. So I guess just to kind of point out, right, it's the force that Q1 has on Q2. So because of Q1, it pulls Q2 this way. Because of Q2, it pulls Q1 that way. So that'll be helpful when we have more than one object in our problems. Okay, so I wanted to bring you to the simulation website, OPhysics, to take a look at our 2 particles A and B. Each grid mark represents 1 meter. And right now I have them 8 meters apart. And just want to kind of look at some relationships here, and you can look at the graph. But right now it's 8 meters, and the electric force between them is 143.63 newtons. Okay, so this is their charge, 10 to the minus 4, one's positive. Let's see, A is positive, B is negative here. And so if we just use Coulomb's law and using the electrostatic constant, we would get our value of 140.63. So I just kind of want you to look at the relationship here. So if I move them to where they are 4, okay, so now instead of being 8 meters apart, they're 4 meters apart. You can see that it jumped from 143 to 160, or 562.5. So that's an increase of 4. So we decrease the distance by 2, we increase the force by a factor of 4 because of the r squared. So you can see that in the graph on the right. And once I reduce this to 2, you see it increases by another factor of 4. So now it's 2,250. If I increase them to just 1, it goes all the way to 9,000 newtons. So it is totally inverse square relationship here. Whereas if I were to reset this, you know, you can see the direct relationship. So you can actually see this is getting smaller because it's getting close to 0. So that affects the force of both of them. So this is a direct relationship. You can see now if it's positive, they're going to change the directions here. I think 10 is the largest number it lets me go. Okay, but it's a direct relationship. Okay, so with some practice, the charge of sphere 2 is twice that of sphere 1, which vector below shows the force 2 on 1. So I think you remember getting these types of questions when we were doing gravitational force. So don't fall for any of this right here. Remember that the force between these two has to be the same. So we're looking for something that's going to be equivalent in size, opposite in direction. How do I know it's opposite? Because they're both positive here. So it looks like the correct answer should be B. Looks to be the same, about the same size and opposite direction. All right. Okay. But now they're decreasing the distance by 1/2. Okay. So now it should be 4 times as large, right? Because if we have basically 1/2 in the denominator, let's see, that's like Q1 and Q2. We have 1/2 squared, that's going to give us a factor of 4. And this one right here looks to be about 2 times as long. So the answer can't be C. So the answer is going to be D, none of the above. It's got to be 4 times as long. Okay. So which of the 3 right-hand charges experiences the largest force? All right, so we have big capital Q is the same in each of these. Then we have small q, and we have the distances vary. Okay. So remember, this is a direct relationship. So 2q is going to have twice, but it is twice as far, right? So you would have, I'm just going to write the differences here, but you have the 2r squared. So in total, that's going to be half as large. Okay. Half as large as this one. So it's not going to be the second one. And then this one, well, now we have 4q. And we have 2r squared. So they're going to end up canceling out, really, because it's going to be 4 over 4. So these two right here are going to be equal. So that would mean our answer would be E. Okay, this is a similar type of question. Which one is going to have the largest force? So we're going to use this as our standard one. So we've already seen this one before, where double the distance and double the charge. That's going to result in half the magnitude. That's not enough. Obviously, keeping the same charge, increasing the distance, that's going to make it even weaker. But if you look at C, it's not only is it close by at R, but it's also double the charge. So that is going to have twice the amount of force as of A. So that's going to have the most force there. Okay, now this one, we're still looking at the black dot, and this time it tells us that the black dot is positively charged. And that's going to be important because we're looking at negatively charged and positively charged. So we really just want to look at how these other ones affect the positively black charged one. So what is this negatively charged particle going to do? Well, it's going to want to pull the positively one towards it. So it's going to pull it this way, to the right. What's the positive one going to do to this positive charge? Well, it's going to repel it. So it's also going to push it that way. So in total, we're going to get a pretty strong force to the right. Okay, whereas these other ones, let's take a look. I mean, remember this is positively charged. The negative one is now going to want to pull it this way. and the positively one is further away, you know, maybe double the distance. So it's going to be repulsive, but much weaker. So that net force is going to be, you know, to the left. All right, this one we're going to have pretty strong repulsive force, and then a weaker one. This one's going to have a much weaker. So we're going to have a leftward force. It's going to be, you know, a little bit like this, but it's not as large as R1 and A. And indeed, these are going to end up canceling out because we have this force, which is going to pull it to the left. This one's going to pull it to the right. And they're equal distance, equal charge. They're going to end up canceling out. So the one with the largest magnitude of force is A. Okay. Another question like this. The direction of the force on charge negative little q. So we're looking at this one right here. So we have an attractive force from negative capital Q, which is going to be relatively strong. And then we're going to have a repulsive force from positive Q. And it's going to be a little bit weaker because it is just a little bit further away. But remember, the distance matters so much. So in total, we're going to have a net force to the left here. All right, so this is just a one-dimensional question, so there's no way that we would get up or down or anything like that. I totally messed up. Yeah, let me start that over. So I totally forgot. This is repulsive, duh. So this one's repulsive and this one's attractive. Sorry about that, guys. So yeah, so we do end up with a net force right there. All right, now we can move on. Okay, so let's walk through this question. So this is similar to the ones that we've looked at, except for now we have like real math, which is kind of nice. Just remember that this means 10 times 10 to the minus 9 coulombs. All right, we're 2 centimeters apart. That's 10 to the minus 2 meters. All right, we've got to use our SI units or else everything will be wrong. So Q1 and Q2 are 10 Newton nano coulombs, and they're both positive. Q3 is smaller, as 1 nanocoulomb of charge, and it's midway between them. They're all positive. Okay. So for this first scenario here, if Q1 and Q2 are equidistant, and you know the same force, they're going to end up canceling out. So we're going to be in electrostatic equilibrium here. So the net force is 0. The second part of the question, they're changing Q2 to now be negatively charged. Okay. So the magnitude of the force 1 on 3 and 2 on 3, they're going to be equal in magnitude. And they're both going to be in the right. And the reason why they're equal in magnitude is they have the same amount of charge. One of them's the one on Q2 is an attractive force, while from Q1 is a repulsive force. So we're going to be adding those together here. So for part B, we're just using the electrostatic constant, 9 times 10 to the 9. And then we're putting in the charge of Q1 and Q3. And you could do the force 2 and 3, doesn't matter since they are the same. Okay, but yeah, so Q1 we said was 10 times 10 to the minus 9. So that's its charge, that's Q1. And Q3 is also 10 times 10 to the minus 9. This is Q2. And they were 1 centimeter, so that's 0.01 meters squared. So this is the force. It's still pretty weak. And because it's 2 of them, if you multiply this by 2, then our net force will be 1.8 times 10 to the minus 3 newtons. It'll be to the right, right? So that's our first question using Coulomb's law. Okay, so this question I kind of already have set up for us. But it's another kind of simple question like this, where we're given the distance between them is 1 centimeter. One has a negative charge of -1 nanocoulomb. One has a positive charge of 4 nanocoulombs. So we have an attractive force between these two. And we're just going to use Coulomb's law to calculate the force there. I have this set up for us. So you're just going to input the charge of A and the charge of B. This will give us the magnitude, and then we'll find the direction for them afterwards. Okay, so you should get 3.6 times 10 to the minus 4 newtons. So obviously B on A is going to be to the right direction, and A on B is going to be to the left direction. So this is another type of question that you could see. So there's a group of 4 particles right now, point charges. And we want to know how that's going to affect the charge in the lower left, which just has one charge. So we're going to kind of look at each of these. I guess we can just call them like 1, 2, and 3. And so we're going to have repulsive charges from all of these. So what is 1 going to do? 1 is going to kind of do something like this, some sort of repulsive charge downwards. So this is going to be, we'll just call it F1. And what is F3 going to do? F3 is also going to do something like that, but to the left. And what's F2 going to do? F2 is going to make a diagonal. And it should be twice the length of F1 and F3. I think that's fairly close. And so now we need to just use our vector addition and add all of these together. So F1, F2, and F3. So obviously not perfect, but what we can see is that it should be to the bottom left right here. That should be our net, which is going to be choice B. So this is just a vector addition type of question. Okay, another question that's kind of similar to that is this one. So we have 2 charges on the bottom, one's positive, one's negative. They are equidistant from the charge that we care about. And so we want to know which direction is going to be happening here. And so this one's actually pretty easy because they are equidistant. away, so we know that their magnitude of charge is going to be the same, but the directions will be different. So this charge right here is going to be inducing a repulsive charge in this direction. And this one right here is going to have an attractive force. Something more like, yeah, that could be a little bit better. Something more like this. Okay, so if we add those together, we will get something like this. Okay, so our F net will be to the right. Be choice D. Good. So here's an interesting question for you. We have a charged plastic kind of sphere in a glass bead at rest on the table. It's only 1 centimeter apart, and the bead has a mass of 15 milligrams. And so we want to know, is the glass going to be able to, quote unquote, leap up to the plastic sphere? Basically, is the electric force strong enough to lift this plastic bead off of the table, or is gravity going to keep it in place? So basically, we just need to look at the weight force and electrostatic force. Okay, so yeah, so we're just going to find these values here. So if you're confused of how they got this, so remember, just write 9 times 10 to the 9. Q1 is going to be minus 10 times 10 to the minus 9, and Q2 be, don't forget the absolute values, 10 times 10 to the minus 9. And then we have our R, which is 0.01 squared. And it was 15 milligrams. So it's 15 times 10 to the minus 3. And for this, we can just use 10 for gravity. All right. I think it was 15 milligrams. Anyway, so if we look at the weight force in the electrostatic force, we can clearly see this number is larger. And it's larger by a lot. I mean, it's larger almost by 60 times. So absolutely, the glass bead is going to lift off of the ground. All right, this question is a little similar. We have two really lightweight honeybees, and they have a really small charge. So this we actually have a P here. The P stands for pico, and that's actually 10 to the minus 12, where nano is 10 to the minus 9. So it's even smaller. So you just have just a little bit of charge. And they are 1 centimeter apart, once again. So what is the repulsive force between the two bees? So we're just going to use Coulomb's law. So we have 9 times 10 to the 9. And then basically we have 23 times 10 to the minus 12 for both of these. And the 1 centimeter apart in the bottom. And this comes out to be 4.8 times 10 to the minus 8 newtons. Okay, and now we're comparing it with their weight. So their weight is just mg. So, I mean, we can really do this in our head. 1 times 10 to the minus 4 times 10 is just times 10 to the minus 3. So the weight force is much stronger than the electrostatic force here. And I mean, in general, the electrostatic force is a very weak force. That's why something has to have an extremely small mass, or be really close, or have a high charge for it to really affect anything. Okay, here's a good question. A small charged plastic ball is vertically above another charged small ball in a frictionless test tube, as shown in the figure. The balls are in equilibrium and are at right now a distance of d apart. If the charge of each ball is doubled, all right, so if the charge was just like q for each of them, if we now make them 2q each, how are we going to have to adjust this equilibrium distance here? So by using our Coulomb's law, if we change, I'll just make a D instead of R. If we double both, then that right now, that's an increase of 4. So how are we going to have to counterbalance an increase of 4? Well, we're going to have to double the distance. Okay, so if we double the distance, it gives us 2 squared, which is 4, so they will stay in that same ratio. So 2d, and that should be just enough. Lastly here, just a quick summary. You know, if you guys have any questions, reach out to me. Just about the fundamental charge, positive, negative, and neutral charges. Charges can't be created or destroyed. Coulomb's law, like I said, super important. Remember, it tells you the magnitude but not the direction. You'll have to know whether or not the particles are both alike or different, whether or not it's going to be repulsive or attractive. That is it for me. Thank you.